So regarding the final paper, it will be 40% for the paper, 10% for the presentation. And the paper itself will be a summary of a research paper that has been published in a journal or a conference. And the paper must have a component related to large sample theory, and it's something you're interested in. So I think I will post some good examples from last year to CCLE, so then you can take a look and see how the paper looked like. So I just encourage everybody to start early, probably after the midterm of this class. We don't have a midterm exam, but after week 5 of this class, so that you know this class well enough and you know which paper you might be interested in picking. So the reason I want to do that is because I think this is more relevant to PhD students' research. You need to write papers, you need to summarize the literature, and this is it. And for the homeworks, it will be 50% of your grade, and we will give you a homework every 2 weeks. So we will ask you to submit your homework electronically to CCLE. Even though you prefer handwriting, you can still just scan it or take a picture of it and then combine your writing into a PDF and upload it. All right, do we have any questions for this class? Okay, yeah, so I also want to say that although we opened the Zoom and we will post the recording and broadcasting the recording, but the default is still in person. So everybody should be here unless you have some specific reasons. If you do, please just let me know. And the Zoom option is a backup. Okay, so then let's get started. All right, so maybe before I start teaching, may I ask you a question? What do you anticipate to be learning from this class? Any volunteers? There must be a reason why you choose this class, right? Maybe for credits or interest. Any volunteers? Maybe you can go. The question is, why would you choose this class? And what do you anticipate to be learning from this class? Right, but what do you think is large sample theory? Do you have any impression of it?
It's something with like asymptotic.
Yeah, exactly. Okay, yeah, then you have a pretty good understanding or expectation of it. So maybe I can ask people here. So how many of you do not understand what asymptotics means? What this term means? One? Just one person. Wow. So other people knows what it means. So, or two. Do you have a guess what it might mean? Could you speak a little louder? Sorry. Mm-hmm. Mm-hmm. All right, so you have seen this term before, but you don't know what exactly it means. All right, how about you? About the same. Okay, so I think to me, I think asymptotic is just a fancy way of saying that you have an infinitely large sample. Basically, that's it. So your sample size goes to infinity. Then what happens, right? So we actually, even though you don't take this class, you should expect that when I have a large enough sample, it means I have the population from which I do sampling. Then it's the perfect case, right? But we know we can never have that large sample. So then we wonder what happens as our sample size approaches infinity. So we care about the trend, and we want to know the rate of the performance improvement as sample size goes to infinity, right? The faster, the better. So that's basically the essence of this class. But I also want to say that, so what we will focus on the most is the distribution of a statistic So here I'm going to use the notation theta hat mean. So theta hat n. So we are talking about the estimation problem here. So theta is the parameter we want to estimate, and theta hat is the estimator we construct from a sample. So n is the sample size. We put it here just to make sure the sample size is something we care about, and it's an important part of this estimator. So we want to understand the distribution of this statistic, or specifically estimator, as sample size n approaches infinity. So in other words, the distribution itself will involve n, but we want to give it some mathematical form so we can track it. So the very famous example everybody knows is the central limit theorem, right? Central limit theorem, short as CLT. And this is the foundation of almost all the large sample theory results we will give you in this class. So what this says is, as n goes to infinity, the sample mean, we call xm bar, minus the population mean will converge in distribution. Actually, in this class, we will use this converging distribution and convergence in law interchangeably, because they actually mean the same thing, to a normal or Gaussian distribution with mean 0 and variance sigma squared. So this is the one-dimensional central limit theorem. In this class, we're going to talk about the multivariate version of it. But just because this is an introduction, I make it simple. So here, the mu is just the mean or the expectation of this distribution. So I just say xi, and sigma square is the variance of xi. And here, x1 to xn are IID, and this xn bar is just their average. So that's the central limit theorem. So you can see that it's about the behavior of the sample mean, right? What its distribution is like. So even though here this x1 to xn, they are IID, but they may not be normally distributed. However, as long as their sample, or I should say, as long as their distribution satisfy an important property, primarily this variance needs to be finite. With this, then the central limit theorem holds. What it says is that when you take the average of these n observations and call the average as xm bar, this xm bar, subject to some centering and scaling, will be normally distributed. And this is something very nice. And that makes normal distribution very important. And we can see a lot of real data follow normal distribution because of this. The reason is that a lot of the measurements we obtain from experiments are some sort of average. Even though we don't measure them directly, but we measure this. So therefore, when we collect many values of this, we'll see these values approximately follow normal distribution. And another important thing from the central limit theorem and what we can learn from this, so these will constitute the following few lectures actually. The first is that, what does this convergence in distribution or in law means? Why do we say convergence in distribution instead of just convergence? That's the first question everyone should bear in mind, and we will talk about this today. The second is that this n, why do we write it this? Instead of writing it as xn bar why is this not good? Anybody can give me an answer? In an undergraduate class, we may not really distinguish the two. We may say, oh, approximately is right, is this, right? But why cannot we write this? Sorry, yeah. Sorry, I cannot hear you well. Can you speak? Yeah, everybody's wearing a mask right now, so it's not easy. Exactly. Yeah. So you cannot have n in the limit, right? Because the limit is as n goes to infinity. Then you have problem here. So basically, this tells us a mathematical rule. That means for the thing that changes, right, in the sequence, you need to put it on the left-hand side. You cannot put it on the right-hand side. So everything related to n must be on the left. So this is something we should keep in mind. Okay. So n cannot be in the limit. That's it. Okay, so this is just a teaser. Now we will start talking about the first basics of this class, which is the mathematical background. And I posted the notes to Cecily already, so you can check the details there. But the essence of this lecture is to introduce several notations widely used in asymptotics. So for today, I'll say lecture 1. So it's the basics. For today, we only talk about, at least for this part, we only talk about numbers. So fixed numbers instead of random variables. Okay, so just numbers, not random. So when things are not random, it's much easier to deal with them. And this is something we might have learned from high school math, right? The sequence of numbers. And so we don't need to worry about randomness. But we are going to use them to introduce some notations. So first of all, right, the most important fundamental concept is the limit. We already used limit here, but what is the limit? What do we mean by a limit? So in this class, if we have a sequence of numbers and we write an converges to a as n goes to infinity, what does it mean? So intuitively, everybody should know that, okay, it means that we have a sequence A1, A2, A3, and they gradually approach A. So it means that whenever I take a neighborhood around A, I should have all the sequences after a certain one to be within that neighborhood, right? And as I shrink my neighborhood, I still have some later part of the sequence in the neighborhood. So that's exactly how we are going to define the limit using a mathematical way. So basically, the definition, formal definition here, I'll just quickly write it as a recap. That means given any, for any epsilon, positive epsilon, I'm going to define a neighborhood around this number. So what I need is that given this epsilon, there exists an integer, n0, that depends on the epsilon, such that I have all the values after this, an minus a less than epsilon for any n greater or equal than this n0. So this is what I said. Given a neighborhood size, we should find a position in the sequence so that all the numbers after that position, this position, are within the epsilon neighborhood of the limit. Right, so we can see that as my epsilon goes down, becomes smaller and smaller, this n0 is expected to be larger and larger. So given this definition of limit, we can define a lot of other things. So the first concept I want to introduce is what we call the asymptotic equivalence. So this is defined between two sequences of numbers, an and bn. So what this means is that even though I may not have an equal to bn for any n, however, I can say AN is asymptotically equivalent to BN. And asymptotic is tied with the limit definition. So essentially, this definition of asymptotic equivalence is just AN over BN converges to 1 as n goes to infinity. So it's defined based on limit. So can I give you an example about what this might be? So one example is that AN is 1 over n plus 1 over n squared. Okay, and here n are just integers, right? 1, 2, and so on. And Bn is 1 over n. So in this example, if you do a simple division, AN over Bn, you can see that their limit is just what? 1 plus 1 over n, right? And then as n go to infinity, it goes to 1. So why is this asymptotic equivalence important? Because it allows us to do some approximations to make the math simpler. So in this case, you see that if I really care about the cases where n is very large, then I can work with Bn instead of An. Bn is a simpler form, so it may make some simplification possible. But An with this form as a remainder, you will get the expression more complicated. So you can think of this whole large sample theory as an approximation. So this is especially important for mathematical statistics, especially in the old days when we need to do a lot of derivations by hand, not by computers. So in this case, simplification often relies on approximation. And these asymptotic tools is a way to do approximation. And we don't want to lose too much accuracy. So that's why this asymptotic equivalence gives us some confidence. That means if your n is large, then you can possibly replace An by Bn or Bn by An, depending on which one is simpler. Does this make sense? Okay, great. Okay, so this is asymptotic equivalence. And another thing I want to talk about is the small o notation. So I'll try to write the O small enough so you can tell it's a small. So when sometimes we write, still it's about two sequences, An and Bn. And we write An is equal to small o of Bn. What does this mean? So in words, it means that An is slower than Bn. Okay, as n increases. But mathematically, it means that An over Bn converges to 0 as n goes to infinity. So we can think of two cases. So if An goes to infinity, or let me simplify a little bit. If both An and Bn goes to infinity, right? Then this means An increases more slowly than Bn does. Then An increases more slowly. This is one case. But otherwise, if An and Bn both decreases and goes down to 0, then it means An decreases more fast. So either way, we know there's something we can play with it. For example, if it's the increasing case, then we can use Bn as an asymptotic lower bound for An. If we have this decreasing case, then we can use Bn as an asymptotic upper bound for An. So both of so we know that in a lot of the statistical arguments, we use lower bounds and upper bound to give us just some best scenario, worst scenario idea, so that we can have better idea about the rate. Because often the rate in terms of n can be quite complicated. So if we simplify it somehow, then we can better talk about it. So for example, what is the rate here in the central limit theorem? It's actually root n, right? So this is just a very good example, but in a lot of cases, we may not have this clean expression. So this big O give us some easy notation. So for example, if I write En is small o, not big O, small o 1 over n. Then what this tells us is that this an goes down to 0 faster than 1 over n. Okay. So speaking of that, let me just give you one example. And this is from the notes. So in this example, because I'm going to use this board only, so I will erase this part. So Christine, it's okay, right? All right. So in this example, we have a random variable x follows binomial with total n and success probability p. And we are under a Bayesian setting. So there's a prior on the parameter p. So assume the prior follows a beta distribution because beta distribution has a support between 0 and 1 with parameters a and b. So I want to give this example because I want to introduce the idea of Bayes estimator. So does anyone here know what a Bayes estimator is? Have you learned this from some other classes? Probably yes, I think. So just as a recap, okay, so the Bayes estimator is just the minimizer. Okay, I'll just write it here. I call p hat Bayes. So it is the minimizer of this loss, the expectation of p hat minus p. This is the parameter p squared. And this is over all possible p hat. And of course, this p hat must be between 0 and 1, right? But the key here is this expectation. In this expectation, we are going to take the expectation over the joint distribution of x and p. So in other words, p is not regarded as fixed, but it's also random because of this prior. And also x is random following this distribution. So this expectation is of joint expectation. And this is different from the I'm going to just say this is the Bayesian point of view, but from the Frequentist point of view, we are just doing is not equal to the argmin of p hat with expectation just on x. So in this case, p is fixed. We're given the true p, we find the p hat minimizing this. So in this case, now in the later case, when we find the minimizer might involve p. It's possible. But if we do this, since p is going to be integrated out, then the minimizer, the Bayes estimator, will not involve p for sure. Okay, so given the binomial and beta, you should be able to do this integration, and then you have a closed form to minimize, and that's the Bayes estimator. So I'm just going to give you the result, and the result is actually a plus x divided by a plus b plus n. So one thing to note is that usually we don't use Bayes estimator in practice. The reason is that, you see, this estimator will involve the parameters in the prior. But in practice, we usually don't know what A and B are. So we don't know the true prior. So there's a way to find the prior to estimate A and B from data. And that's what we call empirical Bayes. So I'm just making a side note here. So if you are doing something like you write down the likelihood from here, from the binomial. You have the prior here. When you multiply them, you have the joint distribution of x and p, and you integrate out p. Then you have the distribution of x given a and b. Then you regard that as the likelihood of a and b given data. You maximize it to find the values of a and b. Then finally, you put those estimates from here, from the maximum likelihood here, into here, this formula, then that's the empirical Bayes estimator. So I'm just saying that if A, B are estimated from data as A hat and B hat, this is what we call empirical Bayes. I'm just making a note here, but this is not something we're going to talk about in this class. But let me ask you then, in this setting, what is my data? The data is just x alone. So we only have one observation, right? And this is the Bayes estimator we obtained from this setting. But what is the MLE? Also a question for you. What is the MLE of P? So P hat MLE, what is it? It should be very straightforward. Right, when we talk about MLE, then the prior doesn't matter anymore. It's just the data and the distribution. So just look at this one. What is the MLE for P? Yeah. And can you say louder? The P itself is the parameter to estimate, right? So the MLE is a function of our data. We want to use the function of data to estimate P, right? What is MLE here? Yeah. X divided by N, right? Exactly. This is something I think if you study at UCLA, this is what we taught in 100B. So X divided by N is the MLE, and this is the Bayes estimator, right? If you compare these two, you can see here prior plays a role. There's no prior. But if you think about N as changing, and you have a large sample size, when N goes to infinity, do they become similar? Given that A and B are fixed. Yes, they do, right? So exactly, so you see the Bayes estimator is basically a trade-off between what we have from the prior. Because you see, given this P follows beta A and B, what we can have from here is the expectation of P, or the average of P given its distribution is A over A plus B. That's what we have from the prior. This is what we have if we only have data, but the Bayes estimator lies in the middle. So whether we tend to go towards the MLE, it depends on the sample size. The larger the sample size, the more alike the Bayes estimator and the MLE. Okay, but if the sample size is very small, let's say only one. So this is actually in this case, I should say, maybe this is something not straightforward, but I should say, even though we only have one X here, but in fact, binomial itself is an aggregate distribution. So it aggregates N Bernoulli P. So basically the sample size here is N instead of 1. Okay, so if it's just N equals 1, then X is binary, 0 or 1. So in this case, you see this prior dominates and the data doesn't matter that much. Okay, so one more thing I can discuss about the Bayes estimator is we can talk about its bias. So you know, one nice thing about the MLE, which we hopefully will talk about later, is that MLE is asymptotically unbiased. And actually in this case, it's exactly unbiased. If you take the expectation of this, you can see it's equal to P. So it's unbiased. But the Bayes estimator is biased. And this is for a reason. The reason is that it's designed to minimize this loss so that it would consider bias just as its component. So minimizing this doesn't necessarily mean the minimizer is unbiased. So often it's biased. And what is bias? Let's take a look. So the bias of this p hat Bayes, I'll give you the formula directly. Is just AP minus BP, A plus B plus M. And let's look at its variance. It's N times P times Q, A plus B plus N squared. Okay, so therefore, you can see what? The bias goes to 0 on the order of 1 over n, while the variance goes to 0 on the order of 1 over n squared. So we can clearly see that the variance shrinks faster than the bias does. Right? So in this case, using this small o notation, we can say variance, right, is small o of the bias. And this also gives us some, well, I would say, justification of, not exactly justification, but some sort of way perspective on that MSE formula. So if you remember, we have this. So this MSE is the expectation of P Bayes minus P squared. Again, this is for the joint distribution of X and P. Okay, so this is what we call the MSE. And we know this is equal to bias squared plus variance. And this is often used as the bias variance trade-off. And then you can see why this square makes sense. Because with the square, then the two terms are in the same order, both in the order of n squared. Otherwise, if they're not of the same order, right? The bias will dominate. Okay, so this is an example to show the small o. But then the question I have for you is, can I say that here the bias of this p hat Bayes, can I say this is asymptotically equivalent to, or say bias square? Can I say the bias square is asymptotically equivalent to the variance? Yes or no? We call that the definition. Is the two things, if I divide them by the ratio, an over bn, that ratio goes to 1 as n goes to infinity. Is this the case or not? Yeah.
I actually have a question.
Sure.
But it's not.
Right. I think I noticed this as well. Yeah, there's an issue with here. Yeah. Actually, I think what I wanted to write. Yeah, that's a nice catch. Because there's an n here, I think I missed that. What should be like is the bias square. Okay, if I square the bias, it's the small o of the variance. Then it's correct. Yeah. But yeah, coming back to this question, is it right? Obviously, it's not. I can give you the answer. Right, so they're not asymptotically equivalent. If you do the ratio, then it's not going to 1. All right, so I think this at least gives you some impression that a lot of in our bias variance calculation, we will involve n in the formula. So we can use n to discuss the convergence rate down to 0. Okay, so for small o, there are several important properties that I want to point out, but I will leave most of them in the notes for you to read, but I'll just mention the most important ones. So first thing is an, if I write it as small o1, it means, right, think about the definition. It means that an is going to 0 as n goes to infinity. That's it. So we have small 1. And second is the transitivity of the big small. So we have if an is small o bn and bn is small o cn, then we will have an is small o of cn. This should be quite obvious. And the second thing is that maybe I should just mention the next one. So if we have another sequence, okay, so Cn doesn't equal to 0. So non-zero sequence Cn, then what we have, if An is small o Bn, we can multiply Cn to each side. So then Cn An is small o Cn Bn. I have that. And also, if Cn is a constant, it doesn't change with n, then we just simplify C doesn't equal to 0, and An is small o Bn. Then in this case, if I just multiply C to An, we don't need to keep C in the small o Bn. So we still have OBN. So basically the small o doesn't keep any multiplier, constant multiplier. It only keeps the things that has an index n. Okay, so finally, it's about multiplication. So if dn is small o e bn, okay, and en is small o cn, then I can multiply both sides. So I have dn en as small o bn cn. Okay, so all these things are quite straightforward and you should be able to verify it yourself. So one more thing I want to say, which are special cases of small o we often see in practices, is, let me just write it this way. So we have, this is important, okay? Some important result. The first thing is that log n, log growth is smaller than polynomial growth. It's always small n of some nk for any k. And we also have, so I should say for any k positive, yeah. So, and also we have nk for any k positive is small o of en, of exponential growth. So polynomial growth is always slower than exponential growth. And log growth is always slower than polynomial growth. So these are some important facts we'll often use. Okay, so far we talked about the asymptotic equivalence and small o. Do we have any questions so far? All right, let me see how we're doing at the Zoom. There's a chat. Okay, got it. Okay, so seems we're good. So Yeah, you can see that they don't cover everything, right? So let me just give you one example. Let's say AN is 2 over n, and BN is 1 over n. So in this case, they don't belong to either asymptotic equivalence or small. So we cannot say your asymptotic equivalent because you take the ratio. The ratio is always 2 instead of 1. So it doesn't converge to 1. And also, we cannot say AN is small o BN or BN is small o AN. So the relations we introduced are not enough. So for this case, we will call them same order. So this is the third relation we are going to introduce. What does same order mean? So you can think about it as the rougher asymptotic equivalence without worrying about the constant. So basically, we write this as the notation. And what it means is that their ratio is asymptotically bounded from both 0 and both infinity. So what it means is that, for if there exists just a lower bound and an upper bound, both are positive and not 0 and not infinity. Okay, so if there are two constants, m and small m and big M, and an integer n0, such that after this index n0, we have an divided by bn absolute value less than small m, or greater than small m less than big M for all n greater than n0. If we have that, then we say an divided by bn is asymptotically bounded. Asymptotically bounded. Okay, with this, then we say they're the same order. So you see, with this definition, because it's bounded above from 0, right? So we can exclude that an is small o of bn. Because it's also bounded away from infinity, we can exclude that bn is small o of an. And this is more general than the asymptotic equivalence. So in this case, we can say an and bn are of the same order, even though they're not asymptotically equivalent. And also, we can say that if an and bn are asymptotic equivalent, then they must be of the same order. So asymptotic equivalence is stronger than the same order. Okay, so that's it. And finally, I want to say something more commonly used than the same order is what we call big O. The big O, I'll write it very big. So it's actually very common. So what it means, it's actually, let's put it simply, it's just the inclusion, or it includes both small o and same order. All right, so I write an as big O bn. What it means? It means that either an is small o bn or an is same order bn. So if one satisfies, then we're good. We can write big O. So basically, you see, what small o means, given this definition, AN is asymptotically smaller than BN. So we can say BN is an asymptotic upper bound of AN. And the same order means that the two things only differ by some finite constant in the limit, right? This is that. So together, it means that we can roughly think this big O as smaller or equal than by ignoring the constant in an asymptotic way. So in other words, this BN gives you a good rate bound on the AN asymptotically. Okay. So yeah, so in the homework, you're going to play more with this. But one special example I can tell you is if I write AN big O1, what does it mean? Here, small O1 means AN goes down to 0. How about big O? So it includes small o, but also bounded, right? So when it's so let's think about this. So it includes both. If AN is small o1, it means AN is going to 0. If AN is the same order as 1, it means what? Given the definition here, it means that AN is bounded. This is bounded, right? So that's what we have. So together, you see, they would tell us that. So together, this implies AN big O1 implies that AN is bounded. That's it. All right. So now we have covered asymptotic equivalence, small o, same order, and big O. And big O is something we use the most often. So again, because it's very general and it gives the asymptotic upper bound sense by ignoring the multiplier, the constant. Oh, mm-hmm. The reason is that I don't care about a small m. Yeah, because with that small m doesn't change my conclusion. Yeah, I'm just trying to decompose what it means, right? So here you already allow it to go down to 0. Then you only worry about whether it goes up to infinity, right? But it does not, so that's enough. Yeah. Yeah, thank you for the question. Okay, so now everything we talk about is numbers. It's about numbers, not random variables. But once we move to random variables, let's see. So now if we have AN, okay, this is a number. If we change it to, I'm not going to use the right arrow to confuse you, to XN. And how about BN? Change to YN. So these are numbers. And these are random variables. Things will become different. What's the major difference? So I think this is something I gradually understand better over the years about random variable sequences. I have to admit that when I first studied those, I just understood them abstractly, not really concretely, but more and more I can really concretize the differences between the right-hand side and left-hand side. So to me, the best way to think about their difference is this. So let me write it down. So first, let me write down the number sequence, A1, A2, A3, and so on, right? So even though we're using notations, but we know each corresponds to only one number. So to make it simple, I can say this is 0.1, 0.15, 0.2, something like that. So I can know they only correspond to one particular number each. But for the xn, each is a random variable. And then when I realize them, each number or each notation can be realized into multiple numbers, what we call observations. So I can think about this as observation 1. The first time I draw observations for each random variable, they may be 0.1, 0.15, 0.2. But when I have another observation, the numbers could change. This may be 0.11, 0.14, 0.21. And then I observe again, maybe it becomes 0.9, 0.16, 0.19, and so on. So you can see that for random variables, their realization could change. And whenever I realize them as a sequence of numbers, the sequence will change. So therefore, all the arguments we have for these things, the number sequence, needs some modification when we apply them to random variable sequences. So the key is to think that their realization will change from observation to observation. So the most important thing to give you a more concrete example, just think about this as just a binary or a coin toss, right? Coin tossing. This is the first toss, second toss, third toss. So we know that when I do the tossing, my sequence could be 0, 1, 0. When you do the tossing, it could be 1, 0, 1. So that randomness is something we want to describe using the random number sequence. So therefore, when we compare two random number sequences, the most important or the most common notations corresponding to what we have here is that the small o here will become small op. The big O will become big OP. And P stands for probability. Okay, so what does this mean? This will be something we will talk about in our next lecture. So when I say xn is small op yn, what does it mean? It means that the probability that xn divided by yn is going to, let me see, the probability that x1 and yn is greater than some epsilon, okay? Maybe I should put it this way. Yeah, this absolute value of xn divided by yn, the ratio absolute value greater than some epsilon, this is going down to 0 for any epsilon. So what this means? It means that for any epsilon neighborhood size, the fact that this ratio is greater than epsilon, this probability will go down to 0 as n goes to infinity. So it means that this is the same as saying the probability of xn yn less or equal than epsilon is going to 1. So these two things are equivalent. So it means that we have a probability approaching to 1 as n go to infinity, that this ratio is very close to 0. So you see that this is something we need to talk about next time. But then this is related to what we mean by convergence in probability. So you can think, why is this a probability? Again, to understand this probability, you need to understand these observations, these realizations. So what I mean is that maybe at a given n, let's say n equals 3. At a given n, so I can calculate the ratio between x3 and y3 for each realization. And I can tell whether this ratio has absolute value less than epsilon or not. So here I will have a yes or no or yes. And then cumulatively, I can tell what this probability is. And what this says is that if I move my n towards infinity, then this probability across realizations will towards 1. So that means in more and more realizations, I satisfy this. And this is convergence. And this is what we mean hold in probability. Okay, so this is just a starter. Next time we will talk more about this convergence in probability. But the basic is to keep in mind that random sequences, random variable sequences are much harder to deal with than the simple number sequences. Okay, so that's it. So another thing I want to say today, it's a side topic, something deviated from what we talk about here, but it's something very good to know because we will use this fact in our later lectures. So this is about the CDF and its inverse. Okay, so CDF, we know what it means, right? Cumulative distribution function. And it is a very important concept when we study the probability because it defines the distribution of a random variable. So here we are still talking about just a real number random variable, one-dimensional. So the CDF Sx, this lowercase x is just any real number, is defined as the probability, or let me be consistent, the probability that x is less or equal than this real number. Right, we know this definition very well. And there are some constraints on this definition. So first of all, it's between 0 and 1. And second, it's monotone, non-decreasing. It never decreases as x increases, but it may stay there. And it may be discontinuous. But it must be right continuous, right? So whenever it's discontinuous, we need to satisfy this. So let me just give you one example. Okay, so let's say that my fx increases right here, but here it doesn't take this value, and there's a sudden jump, okay, to here, and then it goes. So what it means here in this gap. So if I mark this number by x1, then what this means is that I have the probability x less than x1 not equal to, actually smaller than the probability x less or equal than x1. Right, so including x1 and excluding x1 give me two probabilities, and that is the gap, right? Their difference is the gap we're looking at here. So what do we mean here? Actually, we have a name to say this phenomenon. It means that this value x1 has a non-zero probability. So probability x equals to x1 is positive. And we know that when we learn probability, we said for continuous random variable, this probability is always 0. Only for discrete random variable, this is not 0, right? So in this case, even though the distribution is continuous here, but it has a point mass here. And sometimes we do see a distribution like this. So for example, not in this class, but in my other class, we talk about zero inflated distribution, like zero inflated normal distribution. So in that case, what you will have is, so for example, we know in normal, so basically, let me write this. So let's say we have an indicator variable. So when x given z equals 0, right? It's 0. When x given z equals 1, it follows normal distribution. For example, if a distribution is like this, then we look at x alone. And let's say if probability z equals 0 is 0.5, then what it means is that x takes value 0 with probability 0.5. And with the other probability, it will follow a normal distribution. So for a distribution like this, you would have a gap at the jump here. So that's it. And also, sometimes we may have a flat line here. So it means that if you increase your x, your fx stays as this value. So what does this mean? Let's call this x2. So when this happens, it means, let me erase this part. It means probability of x less or equal than x1 is equal to probability x equals to x2. Right? So the probability CDF doesn't increase. And this tells us that basically in this region, there's 0 probability. So this tells me that the probability that x is greater than x1 but less or equal than x2 is 0. So I think we are more used to looking at PDFs, the density functions, than the CDF. But the CDF, the way we show it here, is just to make you realize that it has several scenarios, and we should be able to interpret why there's a discontinuity, why it is flat. Okay, why do we want to introduce this? The reason is that we want to introduce a very important concept later we're going to use in this class, and that is quantile. So the most rigorous way of defining a quantile is as the inverse of CDF. So I have quantile function. And that is defined as F inverse. So if we think about this F as a map, what does it map to? Right? It maps from the real line to the interval of 0, 1, 0 to 1. So its inverse will map So what does it exactly mean? So we know here the CDF is between 0 and 1, right? We go from x to fx. Quantile is the reverse. So given a value between 0 and 1, we want to find a corresponding x. So for example, f inverse 0.5 is what we call median. But this median is different from the median you learn from introductory statistics. So the one you learn is that you have a few numbers, right? You sort them from the smallest to the largest and you pick the middle one. That's the median. And that's just so in our language, that is the median of a sample. So it's a sample median. But what we have here is the population or distribution median. Given a distribution, say Gaussian distribution, you find the median. Given a Poisson distribution, you find the median. And the way to define it formally is through CDF. It's the inverse of CDF. Okay, so then we need to address these complicated issues, right? So let me just motivate you to think. If what is the F inverse P? Is what? and P is between 0 and 1. Given the probability, I want to find its quantile. And the quantile must be some value in the domain of my distribution. So you can see if P is here, very small, in this segment, it's very easy. We just start from P, go here, find the corresponding value. That's the quantile. So problem solved. Because in this segment, it's 1 to 1. But what if my P lies somewhere here, right? So if I start from here, I happen to enter the gap. What's the quantile? What's your guess? What's your rationale? Okay, so as a reminder, fx doesn't take this value, but it takes this value. Okay, so once the P, and so for example, 0.2, 0.4, if my P is 0.3, it just enters the gap. Which quantile should I find it? So I think this is more out of a convention. So we actually pick this one. Pick the one that on the top of it as the quantile. Okay, I'll write this down formally, but you can see we have an expression to summarize everything I'm saying right now. Okay, finally, what if P is 0.5, 0.4? So it just enters the flat line, okay? If I have a P here, you see I have so many values corresponding to fx equals P. What do I pick? We still pick the smallest one, right? So we still pick here. So to summarize what I said, this is defined as the value So we look for possible values so that x value, so that fx is greater or equal than P. It's an upper bound of P. Out of those values, we find the lower bound. And that's the definition of a quantile. Okay, so I think this probably is the first time you listen to how we formally define the quantile, but this will be extremely useful when we talk about sample quantile as a statistic and its distribution. Okay, so I think that's all I want to say for today. And you can check the notes and see that I leave out several things, especially something I want you to read as an after class reading, because we don't give you homework today. It's section 1.2, section 1.2, the embedding sequences. That's something I found it very interesting to read. So it just tells us under which cases does the binomial distribution converges to a Poisson distribution, right? We know this before, but there's some condition. And also you can see that result is itself an asymptotic as an approximation result. And also there is something called Stirling's formula, which basically approximates the m factorial. Right, so, and I think this is also something good to know. All right, so that's all for today. And starting from next lecture on Wednesday, we'll talk about 4 modes of convergence. And these are for random variable sequences. Okay, so see you on Wednesday. All right, so let me stop recording here.